So an alternating series has terms that alternate between positive and negative values. So we can express that as negative 1 to the I, or negative 1 to the I plus 1, times bi, where the sequence bi is all positive, right? So we got a sequence that's all positive, and then we put this negative 1 to the I on it, which makes the terms alternate. Positive, negative, positive, negative, positive, negative. So what would the alternating harmonic series be? Could you write it in sigma notation? And then could you express it out in its meaning, right? So what would the alternating harmonic series? And then write it in such a way that the first term is positive. See if you can do that. Use sigma notation to write the alternating harmonic series. Remember, the harmonic series is a special P series, right? It's the special P series with P equals 1, right? So that's the harmonic series is the special P series with P equals 1. Where is Caitlin Mosier? Did you get the sigma notation for this? What would it be? Right, so it'd just be 1 over. Yeah, that was basically it. Alec, you wanted to answer? Yeah, you basically got it. Okay, so negative 1 to the I times 1 over I. Does that fulfill? But then you get, what's your first term then, if you do that? Yeah, it would be negative. So we need to, what can we do? We need to do, to the I minus, I have I minus 1 or I plus 1. So negative 1 to the either I minus 1 or I plus 1, 1 over I. And then we get the harmonic series, but it's alternating. 1 minus a half plus a third, minus a fourth plus a fifth, etc. Okay, so start writing the sequence of partial sums and think about, will the series converge? So the harmonic series that's not alternating, does it converge or diverge? Diverges. Okay, so let's talk about the alternating harmonic series by looking at the sequence of partial sums. So write out the first 3 or so partial sums. Where's Ruben? Ruben here? Did you get some of the partial sums? So the next one would be a half? Okay. Good, right. So it'd be these, the third partial sum would be these 3, right? So it'd be a half plus a third. And the next one more would be, and I think that's, what is that? 5/6. Yep. Okay. Does it converge? So I think if we look at this visually, we can answer that question. So let's look at this sequence of partial sums visually. We know, what do we know? We know whatever the sequence of partial sums does in the long run is what the whole series will do, right? So what's the first in the sequence? So starting at 0 goes to 1. right? So there's S1. And then we go back a half, right? We go from there, we go back a half, and we end up at a half. There's S2. And then we add a third, and you said that was 5/6? Somewhere up here. And now where I'm at, S3. And then I'm going to subtract a fourth. Somewhere out there. That's S4. What's happening? See, we're honing in, right? So we're always going to add a smaller value than we just subtracted, and we're going to subtract a smaller value than we just added, and so it's just going to keep what? Marching in and kind of honing in on some value, right? So yes. So and we can say it's somewhere between. It's always between. That sum is between any partial sum and the next one, right? You see that partial sum is between S1 and S2. It's also between S2 and S3. It's also between S3 and S4. So take any partial sum and the next one, and the actual where it's converging to has to be between those two. So if we had a really large partial sum, and then we had the next one, then we'd have a really good idea of where it's converging to. Because it'd be somewhere in between those two. All right, so what is it about the alternating series that makes it converge where the alternating harmonic series converged where the harmonic series didn't? Scott?
It's fairly obvious you start with negative numbers. You're not adding constantly, you're subtracting.
Right, half of the terms are negative. This is really going to help for convergence, right? If you have all positive numbers, they're going to have to get small really fast for that to level off. But if every other one is negative, well, now the requirements on that sequence are a lot less. You're getting all that help from the negative terms. Like you said, it's kind of obvious. Okay, so then this takes us to the alternate series test. So the alternating series, -1 to the I minus 1 di, converges if two conditions. If the I plus first term is less than or equal to the ith term, so let's just say, what does that mean? What is that just generally saying about the sequence without the negatives? If the I plus first term is less than or equal to the ith term, then what can you just conclude about the sequence generally? What kind of sequence is that? If the next term is always less than or equal to the one before, then the sequence is doing what? Decreasing, yeah, getting smaller, exactly. The terms are getting smaller or decreasing, right? So we have as long as it's decreasing and the limit is 0. So really, taking these two rules together, we're saying, do the magnitudes of the terms decrease to 0? As long as they decrease to 0, then it converges. Was that enough for just a series in general? If the terms of the sequence decrease to 0? Remember we said the jury was out. But now if you put alternating on that fact, that's good enough, right? That alternating effect, every other one being negative, all we need now is that thing going to 0. And then put the alternating on it, it's going to converge. All right, so here's a couple alternating series. Natural log of 1 over I and 1 over the natural log of I. So use anything that we know so far to see answer whether those will converge or will diverge. Now, to help you, I want to give you the graph of natural log. So here's the graph of natural log. It's asymptotic at 0 coming from the positive side. And then as x increases, it just gets bigger. So it increases this way, and then it decreases to negative infinity as x gets close to 0 from the right. Talk. Go. Work on these. Talk on these. Talk about these. All right, is Cameron here? Cameron. I'll let you pick. Either one. Were you confident about one of those two? The top one. Tell me. Talk to me.
Alright, so we have that it diverges because it's an alternating series, but when ln is smaller, it's going to spread out
Okay.
in the graph because the points are going to eventually become further and further apart.
Okay. Good. So what about, so yeah, it's really about this sequence right here. What's the nature of that sequence? What happens to those values? Really big, negative, right? So then what can we say? This sequence does not do what? Doesn't go to 0, right? That sequence goes to negative infinity. The sequence. And what happens when a sequence doesn't go to 0? Boom, just convergence. So our reason that this one diverges is? It's not the alternating series test, because this doesn't meet the criteria for the alternating series test. So what is our reason that this diverges? The divergence test, which says your series has to go, sorry, your sequence has to go to 0. If your sequence doesn't go to 0, it's over. This thing cannot converge. So this diverges by the divergence test. The divergence test says, if the sequence doesn't go to 0, the series diverges. The only possible way that series can converge, the sum, is if that sequence eventually gets close to 0. Okay? But that's no guarantee. But if it doesn't go to 0, if the sequence doesn't go to 0, like this one goes to negative infinity, then it just automatically, the series diverges. That's what we said at the beginning of class, right? Does it make sense? Okay, what about the second one? Matthew Duplissa.
Okay, I said that it will, well now I'm not so sure, but
Okay.
originally I said it would converge.
Okay, for what reason?
Well, originally I looked at the 1 over ln of I, and then I used that to say that sequence would converge on 0.
Okay.
This is our second criteria.
Okay, so this goes to 0. Does it decrease to 0? Yep. This will decrease to 0. And then what else?
Well, the -1 raised to the n minus 1, that's the part that's confusing. Because now we need to look at the first criteria, which is b, so I plus 1 is less than or equal to b, and I can see that converges.
Yeah, so these two together just say that your sequence goes to 0. Decreases to 0. You have a positive sequence, it's going to goes to 0. Right? So if you have that fact, before we said that's not enough to know it converges. But if you know that and it's alternating, then that's good enough. So converges by the alternating series test. So the first one diverges by the divergence test. The second one converges because it meets the criteria of this alternating series test. Those terms are positive, getting smaller to 0, and it's alternating. That's it. It will converge to some sum, right? So what is the sum? We don't know. Okay, most of these we're not going to find the sum. We can find the sum of geometric series, but most of these we won't find the sum. We'll just conclude if it converges or not. How could we get an estimate for the sum? What could we do to get an estimate for the sum?
Pick two really big numbers and then just look between them.
I think you're thinking about if we had the sequence of partial sums. So if we just sort of looking at the series here, how could we, what's that? Okay. Well, what would we graph though? The sequence? What's that? Okay, so yeah, so if we just had a partial sum for a very large k, right? So some partial sum that takes into account a lot of terms, that would be some estimate of what the whole series was. The more terms that you take, the closer you'd be to the actual sum. Yeah, so if you can look at the sequence of partial sums and you can get those to be pretty big, like the index, like the 100th partial sum or the 500th partial sum, that would be a good estimate. Okay, but for our purposes, we're just mostly going to be saying this converges or this diverges by such and such a test, and we won't know what the sum is. Okay. Questions on alternating series tests? So with if it's an alternating series, now it decreasing to 0 is enough. If it's an alternating series. Before it wasn't, but if it alternates, then it's enough. Okay, let's talk about something called absolute convergence. Absolute convergence. The idea with absolute convergence is, does a series require this alternating help in order to converge? Or will the series converge whether or not some terms are negative? It doesn't matter that some of the terms are negative. It's still going to converge anyway. So some series need the alternating help in order to get them there, like the harmonic series, right? But other series, they could alternate or not, and they'd converge either way. That second category is what we call ones that converge absolutely. If it converges absolutely, it doesn't need the alternating help. Whether or not some of the terms are negative doesn't matter, it will just still converge. So mathematically, we say this, that the series converges absolutely if the sum of the absolute value of all the terms converges. So, right, take away the alternating effect. If it still converges, then it's absolutely convergent, or converges absolutely. Does the idea make sense? Concept? Okay, so then the ones that do need help, or else they won't converge, are called conditionally convergent. An alternating series converges conditionally if the series converges, but not absolutely, meaning it needs the alternating help. So alternating p-series have this form. So for what values of p will these converge absolutely, conditionally, or diverge? All right, so for what values of p will the alternating p-series converge absolutely, conditionally, or diverge? So maybe it will help to look at a couple examples of that. So what about the alternating p-series with p equals 4? So to see, what you do is you say, okay, instead, let's look at this. And what is that series? If I put absolute values around all the terms, I get what series? Convergent or not? Converges because p is greater than 1. Therefore, the original one that we were looking at,
Definitely.
well, converges absolutely. Doesn't matter that the alternating is there or not. So it's absolutely, it converges absolutely. So converges. So the alternating one is absolutely convergent. Okay, the other one, same thing, 1 over cube root of j. First of all, does it converge? Does that converge? So look, we got an alternating series. What does the alternating series test say? If these terms decrease to 0, they do, right? That gets big, right? So because we know 1 over j to the 1/3, the bottom gets big, that will decrease to 0. As an alternating series, that will converge. Now the question is it absolutely convergent? No, because if you put absolute bars on here, now we've got the p series with p equal to 1/3, which doesn't converge. Therefore, this one is conditionally convergent. It needs the alternating help. Without the alternating help, it diverges. Anybody have a question about that? Okay. What about geometric series? Please, yeah. This one? Okay, so if I was to make these all positive terms, then I have the p series with p equal to what? What does the cube root mean? 1 over j to the 1/3, right? So that's a p series with p equal to 1/3. So that diverges. But this converges by the alternating series test. So because this diverges, this can't be absolutely convergent. But it is convergent with when it has the alternating help, it converges. So it's conditionally convergent. Is it better?
Yeah.
Okay. Yeah. Okay, what about geometric series? So does a geometric series ever alternate? It does. When does a geometric series alternate? If r is negative, right? If r is negative. So certainly if r is positive between 0 and 1, we have absolute convergence because all the terms are positive already. So putting absolute value bars doesn't change anything. But what about when r is negative? Between -1 and 0, like this one. Is it absolutely convergent, or does it converge absolutely, or does it converge conditionally? So we look at this. And what if we were to put absolute value bars or make all the terms positive? That's basically what we're saying. If we made all the terms positive, we'd have what series? 7 times positive 2/5, the j minus 1. So this one is, does it converge or diverge? Converges, right? It still converges even when you take all the terms positive. Therefore, this one converges absolutely. Converges absolutely. It doesn't need that alternating effect to get it, the fact that every other term is negative, because when all the terms are positive, it converges. So when is a geometric series absolutely convergent? Yeah, all convergent. So if a geometric series converges, it also converges absolutely. There are no conditionally convergent geometric series. It either diverges outside of -1 and 1, or it's absolutely, or converges absolutely. So for geometric series, there's no conditional, there's no deal where you need the alternating to help it, okay? It's either going to blow up outside of -1 or 1, or it's going to be absolutely convergent. Okay, any questions on absolute convergence? Okay, so there's a test for absolute convergence, and it's called the ratio test. And here's the ratio test. Given a series, we want to set up this limit. Here's the key. We're going to set up this limit right here. We're going to take the I plus first term of the sequence and make a ratio with the ith term of the sequence. And then we're going to look at the limit of that ratio. And we're going to evaluate the limit, and then here are the possibilities. If that limit is less than 1, then the series converges absolutely. If that limit is greater than 1, the series diverges. And if the limit equals 1, then the test doesn't tell you anything. No conclusion. So this is a cool test. Let me show you why this is a cool test. What kind of series is this one, this first one I'm showing you here? Geometric. What happens with a geometric series going from term to term? What happens? How do you get the next term from the previous? And adding 1 to the power does what, Alec? So really, we're doing what? Multiplying by r. Every time we multiply by r to get the next term, right? The previous one by r. Okay? So how can we kind of apply that same thing? Let's think about just any series. Okay, any series. All we know is that we've got these terms of the sequence. So what do we multiply a1 by to get a2? Well, you multiply by a2 over a1, right? If you multiplied a1 by a2 over a1, that would give you a2. Make sense? And what would you multiply a2 by to get a3? a3 over a2. And what would you multiply an by to get the next one, an plus 1? an plus 1 over an. So what's the deal? So with geometric series, what does that multiplier have to be for it to converge? Less than 1, right? So in any generic series, maybe the multiplier changes, right? So maybe a2 over a1 is different than a3 over a2. Sorry, that's not a3 over 2. It's a2. But if we were to look at if this had a limit, then what would we be saying? If that has a limit, it's kind of like it's becoming a geometric series. Do you see that? So this thing is like approaching, if it's approaching some value, it's approaching some multiplier. Then in the end, it's kind of, like I said, approaching or becoming like a geometric series. So what do we want that ratio to do for this thing to converge? We want that ratio to become like a geometric series such that that ratio is between -1 and 1. So it's taking the principle of a geometric series and say, okay, it doesn't have to be geometric, but what if it turns into a geometric series? If it turns into one in the long run, then the same rule would apply. In the long run, if this ratio gets closer and closer to a number between -1 and 1, there it is, then we can say it's It converges absolutely. Why? Because all geometric series converge absolutely. And if that ratio goes outside of -1 and 1, then that's like a geometric series, and we're outside of 1 or -1. And so that we know that will make the series diverge. Does it make sense? So the ratio test is really testing to see if it becomes a convergent geometric series. If it becomes a geometric convergent series in the end, then we know it's absolutely convergent because all geometric series are absolutely convergent. Okay, so let's do some examples. So we're going to set up this thing, the I plus 1 term over a to the I. So I want to have i's. I should change all these to i's. All right, so I'm not going to do it. But so anywhere there's an n, use an I. Okay? Anywhere there's an n, change it to I. In all these examples, I have n's, but we want i's. Okay. So here we go. What is a sub I plus 1? Well, that would be -3 to the I plus 1 over I plus 1 cubed. So that's my I sub 1. A sub I plus 1 divided by a sub I. Which would be -3 to the I over I cubed. So there's this ratio. And we want absolute value. Now, dividing fractions means what? Invert and multiply. And so this step from here on out is where we can start. Instead of starting by writing it as a fraction, we can always start by writing it as the invert and multiply the denominator way. So we can always start this way. -3 to the I plus 1 over I plus 1 cubed times the reciprocal of this, right? Yeah. And when you're starting these problems, you can just always start with that step. So you're gonna write the ai plus first term and then times the reciprocal of the ith term, and it avoids this ugly, very space-consuming step. Okay, and then we're kind of going to look at things that are alike and figure out what we got. So I've got what? I got I plus 1, -3 is on the top, and only I, -3 is on the bottom, which leaves me with what? You see that there's one more -3 on the top. And then what? I have I cubed here over So now here's where we have to, this is a sequence, right? So this is a sequence, and we have to remember back at the beginning of the unit when we talked about evaluating sequences. So what's the limit of I cubed over I plus 1 quantity cubed? What's that limit going to be? So I have I cubed in the numerator, and this is going to have I cubed in the denominator. Does it go to 1, right? You see that will go to 1. That the degrees are the same, and so it would just be the coefficients. But actually, I have a coefficient of 3 up here. So my limit in the end will be, but it's absolute value, 3. So the I cubed over the I cubed polynomial, that just is 1, and then the absolute value of -3 is 3, which is greater than 1. So it's like what this series, those terms are turning into a what? A geometric sequence with r equals 3. Or -3, in fact. So yeah, so it's like turning into a geometric series with r equals -3 in the end, and we know that will diverge. Okay, does it make sense? Let's try another one. Okay, so see if you can do the first couple steps, and we'll work out the end together. So start by, don't make the giant fraction. So start with, first of all the ends are i's. Sorry about that. Make all the ends i's. When you write it down, make all i's there. And you're going to start with ai plus 1 times the reciprocal, or ai, what you're looking at, flipped over. And make that your first step. And then see how. So basically, if we multiplied all this stuff out, we'd have polynomials. What's the leading term of the polynomial on the top? 7. He said 7i to the 5th. Agree? And what about the leading term of the polynomial on the bottom? 7i to the 5th. And then we have a negative 1, which just goes away. So what is the limit? 1. So we need something else, right? So this test doesn't tell us anything. So we go back and we look at this. We've got an alternating series, and we've got 7n squared over n cubed plus 4. So let's look at the limit of that sequence. What's the limit of that sequence? Okay, it's 0. And how does it get to 0, right? So it really gets there. In the end, those terms are like 7n squared over n cubed, which is 7 over n, right? So that sequence, those terms will get like really, really a lot like 7 over n. So we've got an alternating series of basically, in the end, 7 over n. Conclusion. Is it absolutely converges absolutely, converges conditionally, or diverges? 7 over n is virtually the same as? Sorry, I, guys. I. My fault. I know, I told them to change everything to i's. So, but then I kept talking in terms of n, so I don't want to confuse. But anyway, so this is essentially what? The alternating harmonic series. When n or I, whatever you want, gets really, really large, you essentially have 7 times the alternating harmonic series, which we know is conditionally convergent. Conditionally convergent. It needs the alternating effect to converge. If you take away the alternating effect, we have essentially the harmonic series, which diverges. So we practiced the algebra of the ratio test, but really this was a matter for just seeing what we had and comparing it to, it's essentially the same as the alternating harmonic series, which we know converges conditionally. Get started on the web work before Monday. Get started on the web work before Monday. Watch out for the 1 attempt problems.